Good evening. I'm John Schaefer from WNYC. Great to be back at this year's World Science Festival with a program we're calling Good Vibrations, and our topic tonight is sound, the science of sound, which goes from our brains to our inner ears to the universe around us. And we have panelists tonight representing each of those viewpoints. But before we get to the panel, how about some actual sounds? The Polygraph Lounge is a duo comprised of Rob Schwimmer, whose day job is playing the piano, and Mark Stewart, who normally plays the guitar. But when they get together as the Polygraph Lounge, a form of musical mayhem ensues in which all bets are off, and you might see a guitar, you might see a piano, or you might see none of the above. What you will see and hear are old sounds from instruments as ancient as the Aboriginal didgeridoo to new sounds, which come from instruments that the members of the Polygraph Lounge have invented. So to get us started with Siren Song, please welcome Polygraph Lounge.
Long ago, the universe awoke in a beautiful burst of celestial sound. Countless millennia later, at the dawn of humankind, we awoke, opened our ears, and joined this song of the spheres, adding our own exquisite harmony.
Hey, what are you doing?
What? I'm listening to the exquisite harmony.
This is like an urban ear
The
sore.
song of the spheres, man.
No, this is just noise. What do you, this wakes me up every morning.
Haven't you heard of John Cage, the symphony of that which surrounds us, the symphony of the city?
Yeah.
Rob,
What?
Rob, this isn't an urban ear sore. This is the song of the spheres. It's not just what you hear. It's also how you listen. Can I show you?
Do we have to?
I do.
Okay.
4/4 time.
4/4.
Rock and roll. A major.
Okay.
1, 2, 3. There's a brand new dance. It's the best one so far. Just shake your hips, do the bump with a car. When the car starts to say, somebody's stealing me, that's the time you do the dance, the music's loud and free. Before I teach you the dance, gonna play you the tune by a loud and famous artist with a crass, obnoxious croon. But when I show you how I hear it, you'll want to dance along. Adventures to Varese to reveal the Siren Song. See what I mean?
Okay, all right.
Yeah, hey,
cool.
we'll teach him the dance.
Is it dance?
The first move is do the rodeo. Come on, hands over your head like you've got a big lasso. That's it, don't let that doggy go. You do the rodeo. Good. Then patty cake. That's it, come on, patty cake. Yeah, patty cake. Right on. Yeah. patty cake. That's beautiful. Then you do the crawl, like you're swimming to the mall. Yeah, that's it. Yeah, you do the crawl, y'all. Excellent. Very nice, very lovely. Then, everybody, you do the clock. Go ahead and pop it. Yeah, do the clock. Yeah, right on. Okay, then, you make them stop. Like a cop doing aerobics. You can get kind of three-dimensional. Just watch out for your neighbor. That's it. Right on. Excellent. You'll see how this is all used in a moment. Then the last one, monotheistic guilt and release. Ooh. All you polytheists, just fake it. Yeah, okay. We're gonna go around again, and then we're gonna do the dance with the car alarm. A 1, 2, 3. Most tunes that you know they only got one groove. But this one's different. You're busting 6 moves. But when the tempo changes action, don't you give it a damn. It's not Janet Jackson, it's Merce Cunningham. Do the rodeo. Come on. That's it. Then patty cake. Ha! Do the crawl. That's right. Do the clock. Make him stop. Monotheistic guilt. So next time you hear the common car alarm, don't you curse the town, wish you're back on the farm. You just turn to your neighbor, say, I know what this is. It's a brand new dance. It goes like this. Do the rodeo. Yeah. And patty cake. Yeah. Do the crawl. Everybody do the clock. Yeah. Make them stop. Monotheistic guilt. Thank you so much. I'm so glad to be here.
Thank you very much.
And I think we have some colleagues who are going to join us here with all these wonderful sound makers.
Rob Schwimmer, Mark Stewart, Polygraph Lounge.
Welcome.
And let me introduce to you most of the rest of the panel. To my immediate right, Jamshed Bharucha. Jamshed was with us last year on a panel that talked about the neuroscience of sound, and he is a neuroscientist with a particular interest in how our brains process music. He's also provost at Tufts University. And to his right is Christopher Shera, who is a physicist who specializes, let me make sure I got this right, in the peripheral auditory system, which I take it means the ear.
That is correct.
Then why didn't you say so? He is also an auditory physiologist, and to his right is Mark Whittle, the astronomer who is a professor in the astronomy department at the University of Virginia in Charlottesville. And last but certainly not least, Jacob Kirkegaard, or I'll say Kirkegaard here in the States if that's okay, who is a sound artist from Denmark who has actually kind of a scientific bent to his approach to sound. So everybody here tonight, very concerned with sound. We are a kind of a visually oriented species, though. So I think it would be kind of interesting to hear each of you talk a little bit in turn about why sound is important, and especially, Jamshed, why it would be important in a field like neuroscience, which we think of as very abstract and, again, kind of visually oriented, looking at scans and things like that. How did you get interested in sound?
Sound is key to communication. Really, even before we were able to read and write, we communicated by sound. Speaking to each other. History was carried along in an oral history, which was very much to do with sound, and with poetics. And animals have sound as well, that they use to communicate. So sound is a glue that holds individuals together into groups, because it enables them to communicate, to recognize their species, to court each other, and so on.
And we hear in the womb, we hear in utero before we can see. So
we certainly do.
So is our hearing actually, is it primary to
seeing?
Well,
I would say it's primary, but I would say that by the time you're born, in fact, there is some learning that has gone on, auditory learning. And so an 8-day-old infant, for example, shows a preference for the language of its mother, even if it's spoken by somebody other than the mother, compared to some other language, because those patterns of sound have been heard before.
Wow, as early as 8 days.
Mm-hmm.
Chris, you specialize in the way that sound is getting into the brain. You know, is there some secret to the way sound unlocks, you know, through the ear to unlock that mechanism to make us human that way?
Well, I guess I'm not entirely sure about that, but for me, one of the reasons that sound is especially interesting, and I guess hearing in particular, is that I think that they played a really seminal role in the history of science, actually, in the sense that it was the attempt to understand what the relationship was between the length of a string and the sounds that it produced and the sensations of sound that we hear that sort of first led to the discovery that mathematics could explain aspects of nature, and that sort of laid the groundwork for, you know, science. So here we are today at the World Science Festival because of that.
I'm sure his name will come up, but Pythagoras.
Pythagoras, exactly.
Very early on. Actually, one of the many things that he came up with, Mark, was the concept of a music of the spheres.
Yes, yes.
This idea that the universe had some kind of vibration, that everything was somehow in motion. Was he prescient? I mean, has science proven him right in a way?
I think in many ways, yes. I mean, in astronomy, one really tends to think of using sight or perhaps radio waves, but versions of the electromagnetic spectrum. But in fact, out in the universe, pretty much everything is a dilute gas of one form or another, and it's subject to forces, and in response to those, pressure waves, sound waves move. So astronomers routinely now, for example, study sound waves coursing through the sun. The sun actually has many sets of harmonics. You can study its interior that way, but even galaxies have a dilute atmosphere, and there are pressure waves moving through there, and as we'll hear later on, the Big Bang itself had sound, and it plays a crucial role in the subsequent construction of the universe. So yes, it's really a central idea, I think.
But are these sounds that an inner ear, no matter how
no.
precisely tuned, would ever have a chance of hearing?
No. In the case of the Big Bang, you would be killed instantly. You couldn't hear the sound. In the case of the sun, you would be fried. But some imaginary ear that was appropriately scaled in the right way would indeed hear these sounds. Yeah.
Jacob, your work is in sound. How do you approach sound in a way that's different, say, from Mark and Rob or anybody else who's using instruments and amplifiers and all of that kind of thing?
Mm. Well, I'm interested in sound that we don't usually pay attention to, that maybe hiding or secret or just lying somewhere else or living somewhere else, its own life somehow, and I'm interested in paying attention to that.
So, for example, what?
Well, the sound of our own ear, for example, or sound of abandoned rooms in Chernobyl, where I went, or the Icelandic geysers, the volcanic vibrations, which was something I thought about a lot last days.
I would
when
imagine
I
so. A lot of people have been thinking about those Icelandic geysers and volcanoes lately. But the sound of an empty room, you know, that almost sounds like a Zen concept. What's the sound of an empty room?
Yeah, it's a good question. I think I was recording at the Architect Academy and with the students at some point and discovering how how much sound there is in rooms, and from outside, from inside, from the tubes, from everything. And that brought me to the idea of trying to record sounds that, from rooms that had been used for a purpose but abandoned. And that led me to Chernobyl. And it depends on how you listen, basically, I think. It's not only about, what I'm interested in is, sound is maybe not what they seem to be. Like, I'm maybe also not what I seem to be, you know, it's, or you. Yeah, I think it also applies to sound, that it all depends how we listen, how I listen to you, and how I listen to sound, what equipment I use, for example.
Well, I think that'll probably turn out to be a recurring theme, I think, for everybody here. Rob, Mark, did you guys write that song specifically for this occasion, or was that a pre-existing?
Absolutely.
No,
Yesterday.
a Memorial Day picnic, and the 10th time the car alarm went off and everyone groaned. My wife leapt into the street and improvised a dance to the car alarm, transforming the moment into something wonderful. And at that moment I knew we had to write a song, and we did. And the subtitle is The Rehabilitation of an Urban Earsore. And it's precisely what we're saying. It's how one listens, you know. I mean, so the idea that something that we all find, you know, to be a horrible nuisance suddenly becomes something that we can dance to.
I'm sticking to my thing. We wrote it yesterday.
Yeah. I was kind of expecting a more Ulysses Odyssey kind of thing with the title Siren Song, but, you know, that was nice too. Mark, let's talk about the sort of the basic fundamentals of sound.
Yeah, I think we have some visuals. So, Tom, if you bring up the first image here. We have a sort of a very, very primitive musical instrument. It's this famous tuning fork. So the metal vibrates back and forth, and you'll notice that next to the metal here are little dots. These are molecules, and this is the atmosphere that we're embedded in. And so each time this moves, you can see it compresses, the molecules get close together. Now, you want to think of this perhaps as a crowd of people, and they are bashing their neighbors. So there's a crowd surge effect. So these molecules bash their neighbors and so on. And there's a propagating pressure wave here where you can see the gas molecules are bunched up. And between there's fewer. So we say these are the compressions, and in between there are the rarefactions. And the waves move to the right. I'm sorry, this isn't actually a movie, but you just want to imagine these moving. And so there's a bit of terminology here. As these pressure waves move out and ultimately hit your eardrum, the number that hit the eardrum per second is the frequency. And the space between the two peaks here is called the wavelength, and the whole thing propagates along roughly at the speed that the molecules themselves are moving. So the speed of sound is typically the speed with which molecules move. And that's sort of what a pressure wave is. It needn't be the air, it could be water, it could be solids, and so on. And I think it's the big green button, we'll see. Yes, it is, that's good. So there are sort of three aspects to sound it's worth us just sorting and separating out. So the first would be pitch, and pitch is determined by that frequency. And here sort of is a piano keyboard from the bottom of the piano to the top. And over here are those numbers of waves hitting your ear per second. 30 hertz is the name given to this. 100, 1,000, 3,000. It's a bit of a scrunched scale. And the human range, what your ear responds to, is from a little bit below the bottom of the keyboard, 20 hertz, up to about 20,000 or 20 kilohertz. Here, of course, is the musical staff correctly placed against the notes. And here are two, just to give you that idea. Let's, Tom, if we can just play the top one of these. So that was 600 waves hitting your ear per second. And let's just contrast that with this, 200 waves per second. It's a deeper pitch. So obviously the fewer the cycles per second, the deeper the pitch. That's the first quality of sound. That's frequency is related to pitch. What about volume, loudness? This is a quick sort of graph of a pressure wave here, high pressure, low pressure, high pressure, low pressure. So the loudness is defined by basically how much pressure variation there is compared to the average pressure, but in math terms it's delta P over P. The thing that's really interesting about this is that our ears are amazingly sensitive. So for example, if that range in pressure is 1,000th, not a lot. That's essentially deafening. And on the decibel scale, 135 decibels. That's a jet engine. You're close to the engines. A millionth of a difference in pressure is pretty noisy. That's a party sitting in a party in a crowded bar. And then our ear is very quiet. 15 decibels is a billionth. So I think, as we'll be hearing from Christopher, it's very interesting that the ear is able to amplify such tiny, tiny pressure variations. We have very sensitive ears. And then the final quality of noise is its timbre, to use a musical term, or quality, to use the physics term. And that is that nearly all sounds that you hear, including my voice right now, have many, many pitches present, many, many notes. So this is just, here's our frequency scale with low to high. And this is just a particular broad spectrum which sounds like noise. So this spectrum, so loudness up here, for all the different pitches, there's a different loudness. And let's just play this, Tom. So it's just like noise. But of course, music really has a very different quality to our ear. So here's now two spectra of two different instruments. Sorry, something happened there. Let me go back. There we go. So you'll notice that we have two spectra for a clarinet and a flute. So here we have pitch along the bottom. Here's the whole range for a piano, and it goes above that up into the highest notes. And why don't we just play the clarinet now, the top one? So our ears really hear a particular note. And look at the sound spectrum. Here's loudness, and at this point here is a strong spike. Just that tone is present. It's called the fundamental. But then look higher up. All these other spikes, they're called harmonics, and they're what define the particular quality that a clarinet makes. So let's contrast that and play the flute. See, they're playing the same note. They both have this 370 hertz component, but notice how the harmonics are different in the two instruments. That's what makes a flute, and a clarinet, a clarinet. And of course, these harmonics depend on the structure of the instrument. Notice, for example, there's the second harmonic is really present here. It's just absent there. It's quite a difference to do with the way this end is either closed or open. So those are the sort of three qualities that it's nice to keep straight in one's mind.
So the idea that what makes your voice different from my voice, if we're both saying or even singing the same note, is the subtle differences in the harmonics in our respective voices.
Exactly, and in fact, of course, our voices are rather like a flute in the sense we have a column of air. So the typical kind of sound coming out of a human, if I had a spectrum of a human voice, it would be very much like that spiky musical note rather than the noise category.
If you don't have these kind of neatly defined harmonics, is that when you get into noise?
Yes, as soon as you start broadening them, hearing a spread of tone, our ears somehow immediately, our experience is that of noise rather than of note, tone, melody, richness, those sorts of things.
You know, how does, Jamshed, we talked last year about acculturation, you know, learning to expect different sounds, to perceive them in music, depending on what culture you've grown up in. Can we learn to hear things that other people hear as noise as musical?
Yes, we can. I believe we can. There are certain kinds of sounds that perhaps we're most predisposed to hear as music. And for example, you find the octave is pretty universal. But beyond that, there is a lot of cultural relativity in how the various building blocks of sound are put together to make music. If you choose to make music out of noise, who's to say it's not music?
Polygraph Lounge, do you have something you can contribute to the conversation about music and noise?
Yeah, well, I mean, one man's trash is another man's treasure. You know, I mean, when Ornette Coleman first showed up and started making sounds, a lot of people thought what he was doing was making noise, you know, and he was doing things that sounded a lot like this. You know, free jazz as we know it. And some people said, I'm interested in that. A lot of people said that's noise. But I would say, when we were talking earlier about the womb state, our first lessons in listening, and our first lessons perhaps in rhetoric, were in the chaos of the world. Chaos, in quotes. So is not free jazz something closer to a womb state, perhaps, than Beethoven?
Now, you guys have a song about this topic that you can do for us.
Yeah, we do, in fact.
Just happen to have
We
it
just
in
happen to
there.
have a song.
We just wrote it yesterday.
They had a very, very busy day, apparently.
See, I was walking down the street just the other day when my friend turned to me, he started to say,
I'm hearing something strange from like a mile away. That sounds weird.
no, it's good.
Huh? Could it be?
Maybe it could. Could that be music? Could that be music? I don't know. So I said to my friend, if that's music, I know that it's not any music I've heard in our show.
Is that a new melody? Or am I hearing a crow? That sounds weird.
No, it's good.
Yeah? Could it be?
Maybe it could. Could that be music? Could that be music? I don't know. Some music's fast and loud, some music's soft and sweet. It sounds like ooh. Some music's made of noise, sometimes it's just a beat. You wonder. Could that be music? Could that be music? Could that be music? I don't know. I don't know. I don't know. Questions pertain to pedigree. Could this be music? Like that of Tchaikovsky. See, there's a couple of things that we'd like to share. Sometimes with music, you don't really know what's there. But if it makes you listen and it makes you care, then that's good. When you hear, sounds that tickle your ear and make you ask, could that be music? Caw, could that be music? Could that be music? I wonder, could that be music? I don't know. Cause we don't really know, cha-cha-cha. We really don't.
A suggestion that perhaps it isn't all science after all. There's a lot of, Jamshed, a lot of the neuroscience of music is about context, isn't it? About,
Sure.
you know, Mark is telling us about the fundamentals of sound, you know, the amplitude, the loudness, the timbre, the quality of the sound. But a sound out of context is just that. You have to create intervals and things for us to perceive it somehow as music, right?
Absolutely. The context is really key, excuse the pun. But let me just illustrate some of the fundamentals, and then I'll talk a little bit about how context comes into play and how the brain really is a pattern recognition machine that's trying to put all of these different frequencies together to make sense of it. So for those of you who are more sort of viscerally movement-oriented, I'm going to illustrate the notion of vibration and harmonics using just a simple telephone cord. You could use a jump rope or anything like that, but I found this to be the most compelling way to illustrate it, particularly for kids, but for anybody else. Would you hold one end of that? And any kind of object really is going to vibrate, even a bridge. You know, as you go over the George Washington Bridge, it's got a certain vibration. And this, if I just move it, it's going to vibrate in certain ways, but there is a certain speed at which I can get it to vibrate with very minimal movement of my hand. That's called a fundamental frequency, as was explained by Mark and by Chris. And I could do it in 3 dimensions like this, and this is the fundamental frequency of this particular chord stretched in this particular way. So that's the tempo. If I were to change that to be a little bit faster or a little bit slower, it sort of becomes chaotic. Okay, so we'll go back to the fundamental. And now you heard Chris talk about the Pythagoras and mathematical ratios as being really the basis of science. And so the science of sound was in many ways the basis of science. And you heard Mark talk about harmonics. If I wanted to get to the second harmonic, then I can just sort of perturb this chord at twice the speed, okay? So I'll do it at twice the speed and see what happens. It takes a bit to get it. Now do you see that? It's really vibrating in 2 pieces. I go back to the original one, which is the fundamental frequency. So twice the speed creates the second harmonic, which vibrates in 2 segments that cuts the rope in half. Now I'll do it in 3 times, which is the third harmonic, which should cause the rope to vibrate in thirds. 3 segments, 1/3 each. 1, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? Okay? People keep doing it. We keep doing it. Now we can get to the fourth harmonic. Okay? 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Thank you. Now, it turns out, actually, that,
Are you going to spin plates next?
I have my violin here. I'm not going to play a tune, but just to illustrate some of these concepts and then to take 1 or 2 sort of steps forward before getting into context. So just like the telephone chord, a violin string vibrates with many of these harmonics all at the same time. So the first, the fundamental, second harmonic, third harmonic, etc., up to very high numbers of harmonics. They're all vibrating at all of those modes at the same time. And because the second harmonic involves the string vibrating in 2 segments that are exactly half each, therefore the frequency of the second harmonic is twice that of the fundamental. And that turns out to be the octave, which is one of the reasons why the octave is so common around the world, because it in fact is the very next mode beyond the fundamental. And so the octave for most of you is simply and so on. If you go up to the third harmonic, which is where the string was vibrating in equal segments of 1/3 each, that means that the string was vibrating 3 times as fast, so the frequency was 3 times as much. And that creates what's called, for the musicians, you recognize as the perfect fifth. The non-musicians, don't worry about that fifth. It's a confusing name, but think of it as the third harmonic. And if you then bring down that third harmonic into a lower octave, you would divide it again by 2. So this next musical interval is multiplying by 3 to get the third harmonic, bringing it back down 1 octave, dividing it by 2, which means multiplying by 3/2. And so the violin, for example, the strings are tuned in ratios of 3/2. If I start with the lowest string, G, if I multiply the frequency by 3/2, I get D, and then another 3/2, A, and then E, and so on. And consonance and dissonance are very much driven by how accurately you capture those simple integer ratios, 3/2, 2/1, etc. And if you violate those ratios so that you end up with extremely complicated ratios, you go out of tune in conventional terms. Now, you can also learn to like dissonance, so I don't mean to imply that dissonance is bad musically, but dissonance just has a certain quality.
Well, our piano is a completely dissonant instrument because we don't have a lot of those whole number ratios. Everything's been moved.
Absolutely. And so let me just illustrate your point. If you were to go up, starting on the lowest string, by octave, so you're multiplying by 2, multiplying by 2 again, and so on. You can keep going up, multiplying by 2. Or you go up by these intervals of 3 over 2 that I talked about, okay? Multiply by 3 over 2, 3 over 2, et cetera, et cetera. For those, the mathematicians in the audience, you'll recognize this should mean that at some point, as you go up, when going up by octaves or going up by 3 over 2 intervals, there should be some convergence musically. And the musicians will recognize that. If you start at the lowest C on the piano and you go up all 7 octaves, you come back to a C, of course, because they're octaves. But if you start on that same lowest C and you go up to G and then D and then A and E, which are frequency ratios of 3 over 2, if you do that 12 times, you come back up to that same C 7 octaves above. So for the mathematicians, you should be thinking that means that 2 to the power of 7 ought to be equal to 3 over 2 to the power of 12. One of the great mathematical musical tragedies is that that's not true. Okay? The universe has this imperfection in it, excuse my cosmological metaphor. It indeed is tragic that 2 to the power of 7 is not equal to 3 over 2 to the power of 12. And Pythagoras knew this based on string lengths 2,500 years ago. And that difference, that tiny difference between, if you calculate those numbers on your calculator later on tonight, you'll see it's a tiny, tiny difference. That's called the Pythagorean comma. And it caused a lot of anxiety for centuries and centuries and centuries. Because as John mentioned, if you tune an instrument by octaves, then the other intervals are out of tune. If you tune a guitar in one key, then the other keys are out of tune. You have to kind of stretch the strings a little bit to get it in tune. And nobody could really get a keyboard to play in different keys. If you tune the keyboard to one key, then it sounded out of tune in another key. It was really only 500 years ago or so that people came up with a very simple solution. To heck with the simple integers, just fudge them, okay? Sort of 3 over 2, kind of, sort of, plus or minus a little bit, octave is 2 to 1, kind of, sort of. And if you fudge them systematically, then you can tune the piano so that it plays any given key.
Now, what does this do to the way, it had never occurred to me before tonight that 3 over 2 to the 12th power not equaling 2 to the 7th power might be a tragedy. What does this do to, music is about emotion. What does this do to our emotional response to the sounds that we hear?
Okay, so now moving into your earlier question about context. As I said at the beginning of the program, the most important thing about sound from the point of view of a neuroscientist is that we use it to communicate. It's a communication code, if you like, whether it's language, spoken language, whether it's music, whether it's animal sounds. And I've got some animal sounds I'll play you just in a minute. But before that, I want to talk a little bit about an experiment that my former student, Megan Curtis, and I did, we published recently, about the auditory codes that are used in speech to communicate. So what we did is we actually had people come into our lab. They were student actresses, and asked them to speak with different emotions. And we asked them to speak bisyllabic utterances, words like okay, hello, with different emotions. And we recorded the sound, and then we analyzed it on a computer, and we found, much to our surprise, well, to my surprise, my student was convinced that she was going to find this, and I was the skeptical one, but it turned out to be true. That's one of the nice things about science. For sadness, when the actresses were expressing sadness, and we looked at the pitch intervals between the two syllabi, they were overwhelmingly descending minor thirds. And I was surprised by this because most musicians would probably dismiss that notion, but it's true. And so I have an example. If you could play the
Let's go.
Could you play that one more time, please? Yeah.
Let's go.
That's a descending minor third.
Bum, bum, that interval.
Yeah. Now, we don't actually think consciously about the pitch when we listen to speech in a familiar language because the meaning just sort of pops into the head after the brain goes through all of those levels of processing. And I'll play you an unfamiliar language in a minute to show how you do, in fact, focus on the pitch. But in this case, it's only recently that we've been able to analyze these sounds using computers in ways in which we can actually pinpoint these pitches in stable enough ways so we could map them onto musical intervals. However, for anger, we got a very different code. Could you just play anger, please? The anger example.
Let's go.
Okay. That's an ascending minor second, ascending semitone. We found the code for anger was actually bimodal, which means that there were two different intervals, ascending minor second and an ascending augmented fourth. For the musicians, you know that's the tritone. And what was interesting is that for the positive emotions, sadness and anger both being negative emotions, for positive emotions, we found no pitch code at all. There were no favored intervals at all, which is an interesting finding. And what we interpret that to mean is that through evolution, it was important that you be able to communicate negative emotions very accurately because there are consequences to negative emotions. You better understand if somebody's angry. You better understand if somebody's sad. There could be consequences for that person. But if they communicate happy emotions, there aren't the same kinds of consequences evolutionarily, and so there's no code.
What about animals? I mean, cries of alarm? I mean, you have to be able to recognize that.
Absolutely. And so many of you have heard many kinds of animal sounds. Obviously, I have for you a sound of wolves. It's really extraordinary. I mean, speak of music, I think actually that's music. You hear it in a minute. But animals have used pitch codes, for millions and millions of years. So could you play the wolf example, please? That's one wolf. Now, as soon as another one hears it, it starts to echo back. Probably cut it off there.
Can I hear the car alarm again?
The thing about...
Is there a way to interpret what the meaning of that is without being an animal behavioralist?
Well, not the specific meaning in any kind of linguistic way, but animals use sound like that, in this sort of chorusing way, to develop social coherence and cohesion, excuse me. And so wolves can actually recognize each other from miles and miles away. So it is a kind of a communication, a signaling, and they can acknowledge, who's present, who's still around, where you are, and sort of raise their hand and say, I'm still part of the community, I'm here. It's an extraordinary way to bring people together. And I would argue music is really also a form of fostering social cohesion. People who have the same musical interest, people who, tribes who have the same kinds of songs and dances, engage in that as a way of forming these social bonds, of defining those social groups that are so powerful for success.
So does language get in our way if we want to communicate with groups from, I mean, you know, we heard, let's go, you know, and we understand that both on a literal sense, but also on a kind of musical one. I mean, you have an example of an unfamiliar language.
Absolutely. Now, one of the most thorny issues in modern theoretical linguistics is the following. Why don't all human beings speak the same language? Okay? Think about it. It's actually a sort of a shocking phenomenon in evolution that we evolved the ability to use language which has actually the same underlying syntactical structure universally. All languages, not just spoken, but even manual sign languages, have the same underlying syntactical structures. But the auditory codes that are used, the acoustic codes that are used, are radically different. And you know, I won't go into the reasons that have been suggested for why that might be, but that has really created a path for the creation of new cultures and new languages and divergence, and the naming of new kinds of objects that may not have been around if language is generative or creative. And so if different languages can evolve with completely different sound patterns, then you can do that. So I'm going to play you just a sample of another language that I know, Hindi, which is maybe unfamiliar to most of you. And as you listen to it, you'll be conscious of the fact that all you hear is sound, because it doesn't mean anything. When you hear a language spoken in your own dialect, in your own accent, and with your own linguistic community, you really don't pay attention to the sound. The meaning just pops right into your head. So could you play the Hindi example, please?
जनता दल के अध्यक्ष लालू प्रसाद यादव को आय से अधिक संपत्ति रखने के मामले में जमानत न मिलने के बाद 14 दिन की न्यायिक हिरासत में भेज दिया गया है। उन्हें बेऊर जेल में रखा गया है। बिहार
For those who know Hindi, the meaning pops into your head, and you don't pay attention to the sound. But for those who don't, all you're conscious of is the sound, because the brain hasn't been able to use that code to do advanced levels of processing to get the meaning out the other end.
Is that why we always think people who speak other languages, I mean, I've always thought French is a very musical language. I think Norwegian is a very musical language. Is that why? Because we're hearing inflections that the native speakers might not even?
Absolutely. We rarely are aware of the sound patterns of our own language. And then when somebody deviates, we say, oh, they have an accent. Well, there's no such thing as an accent. It just means they're using sound patterns that are different from the ones we're used to using. And the same would be in the case of music. So we have the capacity to develop different kinds of music in different cultures. And if you aren't accustomed to that, if you're not familiar to that, then the sounds can sometimes be experienced as sort of an accent or some as unusual, sort of weird in some way. And when you listen to music that you're very familiar with, again, the brain processes it very automatically because the brain is familiar with the underlying structures, with the timbres that are used, and you start to hear different kinds of things in it. Whereas if you're unfamiliar, all you hear is sort of the surface sounds. I'm going to play you an example of classical Indian music. A lot of people say music is the universal language, and in a way it is, but I think it's a cliche. It's used too often and too readily. In my experience, very few Western classical musicians, except of younger generations, really are able to appreciate Indian classical music and vice versa. So there really are cultural differences. You asked about context, and let me give you a demonstration about how the brain hears sound in a highly contextual way to try to make sense of it. The brain is basically a pattern recognition machine. It's desperate to find patterns. It doesn't like just random sounds or sort of random. It tries to find patterns, and sometimes they're illusory. Sometimes it sort of grasps at something that isn't there. So I'm going to play you a sound. It's just sort of like well, you can hear it for yourself. Could you play me number 1, please? Anybody want to say what you heard?
Bird song?
Bird, okay. Could you play me number 2, please? Another bird, maybe? Whistling?
Whistling.
Radio, okay. Number 3?
R2D2, yeah.
Okay, now if we combine those 3 sounds, could you play me the 1, 2, 3 example, please?
Where were you a year ago?
Hey, what did you hear?
That sounded like...
Can you play it again?
Where were you a year ago?
Voice.
Play it one more time.
Where were you a year ago?
Where were you a year ago?
Okay, one final time.
Where were you a year ago?
Okay, where were you a year ago? Okay, now, so each of those little bird kinds of phrases, we combined 3 of them, and we got speech. We got familiar English language speech. And that's because the way this was synthesized is we started with speech, and I'll play you the original from which this was synthesized. Could you play me the natural speech, please?
Where were you a year ago?
So somebody actually said that into a microphone. Okay, we analyzed on a computer what's called a spectrogram and traced the energy peaks over time, the 3 most prominent energy peaks over time, which are called formants, or resonances on a musical instrument. They're where most of the energy is. And we trace those peaks as sine waves, and then just combine them. And the brain, if it gets into its speech mode, when you weren't in your speech mode, all you heard was these sort of 3 bird calls combined. But as soon as somebody heard it as speech, and you said, oh, speech, where were you, where? Suddenly, whoa, you hear it. And then if you were to hear other speech in this way, you would get it almost immediately. So the brain is really putting pieces together in ways that it might find to be familiar, and then creating an illusion. This is an illusion, illusory speech, that is in psychology sometimes called a gestalt, where the whole is greater than the sum of its parts, and then you no longer hear the individual whistling or bird sounds, you hear the whole thing. This is not my research, this is the work of Robert Remez, who's here in New York at Columbia. It's really, really interesting stuff. You can actually synthesize sine wave music, which is sort of cool to listen to. And it's very much an analog of visual illusions that many of you may have seen in psychology 1 courses and so on. Could you please put up my first slide, which is a visual illusion, very common illusion there. Do you see sort of an invisible triangle popping out?
Yeah.
Yeah, so, and you can actually see the contours of the triangle. They're called illusory contours. And even though there are 2 triangles here. One is bounded by those angles, those vertices, but the sides are not continuous, and you can see them sort of filled out. The other triangle is bounded by those little mouths of these pie things, and that one is almost not defined at all, and yet it pops into your mind as an illusory contour. Again, it's the brain making sense, trying to find familiar patterns and things. That's very much how the brain works.
So
yeah.
I think maybe at this point, the point of the brain as a pattern recognition machine seems to me a great segue, Chris, to how the brain gets to hear those patterns, the mechanism by which the brain gets that information that it can then process and look for patterns and stuff. And this seems to be where you come in with the peripheral auditory, whatever it was that you called it.
The peripheral auditory system. Yeah, and the reason I say peripheral auditory system as opposed to the ear is that many people, I'm not necessarily among them, believe that the brain is actually very important for hearing. Obviously it is, but since my focus is on the peripheral auditory system, in other words, the part which is before all the neurons, I wanted to distinguish that the ear is just simply more than the part that we see on the outside.
And in fact, it seems like it's the inner ear that is the area full of surprises.
Yes, that's absolutely right. In the time of the ancient Greeks, people believed that the way vision worked was that there was, in a sense, a fire within the eye, and that the way that we saw was that beams of light came out of the eye and contacted objects, and that enabled us to see them. And of course, we no longer believe that that's the way vision works. But the amazing thing is that it seems to be, with appropriate modifications, the way that the ear works, that the ear creates sound in order to help it perceive sound. So I have some slides on this topic. Yeah, so here we see a diagram of the ear. We have the external ear over here. And hearing begins when sound waves travel along the ear canal here, and they vibrate this membrane, the eardrum. And that vibration is then transmitted by these three little bones of the middle ear, the three smallest bones in the human body, to this spiral-shaped structure here known as the inner ear or cochlea. And it's the purpose of the cochlea to change the energy carried by sound into neural impulses that are then transmitted along the cochlear nerve or the auditory nerve to the brain. And of course, the brain interprets those neural impulses as sound and speech. So if you imagine taking this spiral structure here and uncoiling it, you might get something that looks like this, idealized version of it. Basically, the inner ear, when uncoiled, consists of two fluid-filled chambers, an upper chamber and a lower chamber, separated by an elastic membrane. And the vibration of the middle ear bones, not shown here, sets these fluids inside the cochlea into motion. And that launches a wave which propagates down along this elastic sheet to a region where the motion is largest and beyond which the wave dies out quickly. And this wave is pretty much, it's not a sound wave, but it's more analogous to a wave which might propagate on the surface of the ocean. For an ocean wave, the reason that the wave propagates is there's an interaction between the moving fluid and the force of gravity. And a similar thing happens here. There's moving fluid, but the force is not gravity. The force is the stiffness of this elastic sheet. And because the stiffness of this elastic sheet varies as a function of distance along the cochlea acts as an acoustic prism, separating the various frequency components of sound out and mapping them onto different places along this membrane, and thus onto different populations of nerve fibers, because the nerve fibers contact different places along this membrane. And so it's in part the fact that different sounds stimulate different nerve fibers that allows us to separate out and to hear different notes. So one of the amazing things about the cochlea is its extreme sensitivity. It turns out that at the threshold of hearing, in other words, for the quietest sounds that we can hear, this membrane, this elastic sheet, moves up and down by less than the diameter of a hydrogen atom. And indeed, to make this wave visible on this graph here, the relative amplitude of this wave has been exaggerated relative to the other structures by over a factor of 1,000,000. So the ear contains extremely sensitive, it's an extremely sensitive sensor. Corresponding to that, or in addition to that, it has a huge dynamic range. In other words, the dynamic range of hearing is basically that range of sound intensities over which the ear, or the peripheral auditory system, as I like to say, can usefully encode sound. And it turns out that dynamic range is so large that just quoting a number doesn't really drive the point home. So it's useful to think of an analogy. And so let's represent the range of energies in the softest versus the loudest sound that we can usefully encode, and make that equivalent to the weight of one mouse to something else. So if the energy in the quietest sound is equal to the weight of one mouse, what is it that corresponds to the loudest sound that we can hear? And it's useful, as I show here, to express the answer in elephants. But it turns out that the ratio from the quietest to the loudest sound is not just the weight of one mouse to one elephant. In fact, it's not even the weight of one mouse to 2 elephants, or to 3 elephants, or even to 5 elephants, or to 50 elephants, or even to 500 elephants. It turns out that the ratio of the quietest to the loudest sound is equivalent to the ratio of one mouse to 20 million elephants. It's a number which is so large that if you insist on stacking the elephants vertically like this, you have to take into account the fact that gravity falls off with distance from the center of the Earth. And so this resulting Tower of Elephants is some 40,000 miles high. So we have extraordinarily sensitive detector with a huge dynamic range. And all of this sort of makes one wonder, well, how can the ear possibly do that? And it turns out that the answer that we believe today is that the ear actually contains cellular amplifiers that help boost the energy in quiet sounds. And it turns out that this process of amplification is very similar, has certain analogous features to the way that a laser amplifies light. So how does a laser work? Well, a laser basically consists of some sort of lasing medium. It may be molecules of a gas or a crystal or something, and some sort of power supply or pumping process that can put the atoms in this gas or crystal into an excited state, so that when they relax, they emit incoherent radiation, by which I mean that radiation that goes off in a number of different directions and polarizations and with various phases and so on. But through the magic of quantum mechanics, when you apply an input light to this medium, it induces the atoms in this laser medium to emit in phase with the input light. And as a result of that, these atoms add in phase with the stimulus, and because they're adding in phase with the stimulus, they boost its amplitude. And what happens is you produce an amplified output light medium. So I said that this is very similar to what we believe is actually happening inside the cochlea. So how does that actually work? Well, to understand that, we have to look a little closer into what's actually inside the cochlea. We already know that we have waves propagating in the cochlea, and that's of course analogous to the light waves that are propagating inside a laser. And as I said, we have to look in a little more detail at the properties of this elastic sheet. I've idealized it here as an elastic sheet, but in reality it's actually a very complicated structure. And to see that, you can zoom in a little bit and you can get a more realistic picture of what the cochlea looks like. Here we have these two fluid-filled chambers, the upper chamber and the lower chamber. And this, what used to be the elastic sheet, you can now see is actually this third chamber that contains these cellular structures. And the most important of these are these so-called hair cells. And you can see those if you zoom in a little bit. This is the structure of that elastic sheet in a little more detail. You can see there are many different types of cells. And the most important of them are these cells right here, the ones shown in red, the so-called hair cells. And they're called hair cells because at their tips, they have little hairs or cilia that stick out of the top. And as I said, when a sound is perceived, or when a sound stimulates the ear, this entire structure vibrates up and down. This is this elastic sheet that vibrates up and down when a wave propagates along it. And when this vibrates up and down, these little cilia, the little hairs on top of the hair cells, are moved back and forth. And when the hairs move back and forth, ions flow from outside into the cell. And that flow of ions is driven by essentially a biochemical battery that is maintained inside the ear. So this battery drives current into these cells when the cilia move back and forth. And these cells have an amazing property, that when current comes into the cell, of course, the voltage inside the cell changes, and when the voltage inside these cells change, these cells move. And here we have a movie that illustrates this fact. So here we have one of these hair cells that's been taken out of the inner ear and placed in a dish. And an electrode has been brought in contact with this cell, and that electrode is used to change the voltage inside the cell. Can we play that movie again? And you see that when the voltage is changed inside the cell elongates and contracts. So it moves. And when this cell moves, of course, it pushes the fluid around inside the cochlea. And when it pushes the fluid around inside the cochlea, that generates hydromechanical waves that can propagate up and down. And so this is analogous to the emission of light by the atoms in the lasing medium. But of course, instead of light waves, we have these hydromechanical waves. We have the motion of the fluid in the membrane. So the analogy then with the laser is that we have some laser-like medium. This consists of the hair cells and the surrounding fluid. Here are the little diagrams of the hair cells. And we have a battery, ionic battery, that provides the power supply to this laser. Then, when it's stimulated by an input traveling wave, it stimulates these hair cells to move in phase with that wave and emit coherent hydromechanical radiation that boosts the amplitude of the wave as it passes by. very much in analogy with what happens inside a laser amplifier. So here we have another cartoon of it. Illustrates the fire within the ear. It's not, of course, within the eye, it's in the ear. Here we have the cartoon that shows the middle ear bones vibrating, generating a wave which propagates down. This coherent hydromechanical radiation emitted by these hair cells combines in phase with this wave, boosts it, and amplifying it, enabling us to detect and to hear quiet sounds. So most of you are probably most familiar with a laser, not in the context of a laser amplifier like I've been talking about, but in terms of a device like this laser pointer here, which not only amplifies light, but actually emits light. It turns out that the ear does something very similar. It can also generate sound as well as receive sound. And the way that works is we have these traveling waves traveling down the cochlea, and because of imperfections in the structure of the cochlea, some of this wave energy is reflected back. It travels back, and when it hits the middle ear, it's reflected back again, generates another wave that travels down. We basically have this feedback process where the output is fed back into the input. It's very much like a public address system where the gain is turned up a little too high. You can get annoying feedback, as we were having problems with that in the rehearsal. And so what happens is you have waves building up as they travel back and forth inside the cochlea. And of course, some of that wave energy leaks out through the middle ear and can be detected as sound in the ear canal.
Is that different? Is that different from tinnitus or tinnitus? Is that
generally speaking, yes. Tinnitus is the sort of the perception of a sound which isn't really present, at least not in the environment. And it turns out that maybe in 4 or 5% of cases, people have found that in patients with tinnitus, they can actually record sounds being emitted by their ears. But the vast majority of cases, 95% plus, there is no sound being created by the ear. It's something that's created by the central nervous system.
But you can record these sounds, I guess, as this slide suggests.
You can record these sounds. You can record them with a microphone. I have one of them here. It looks very much like the microphone that we might wear on our lapel, except instead of putting it on our lapel to record our voices, we stick it in our ear canal and listen to the ear. And here I have an example. You can record these sounds from humans as well as from more exotic animals, like, for example, here from the ear of a tiger. Of course, the tiger is heavily anesthetized. It's also very useful that the ear is not immediately adjacent to the teeth. All of these things make it possible to record these sounds generated by the ear of tigers and other animals. And I have an example of some of these sounds, not recorded from the ear of a tiger, but from the ear of a human. And here we have, earlier Mark was showing you sound spectrum. This shows as a function of frequency, basically the energy content of the sound. This is of a sound recorded in the human ear canal. No stimulus has been applied. It's recorded in a quiet room. And these spikes indicate that the ear is essentially making pure tones, whistling, at these discrete frequencies. And chances are, if you have good hearing, your ear is doing something very similar to this as we speak. It's whistling while it works. And this, of course, is created by these waves going back and forth inside the cochlea. And I have a sound demonstration of one of these so-called spontaneous otoacoustic emissions. So that's what the sounds generated by your ear spontaneously, what they sound like. It's not especially interesting, but one of our guests has actually been able to turn that into music. So.
Actually, Jacob, this is like a perfect setup for the piece that we're going to hear from you.
Thanks very much, Chris. Yeah, it was great. Yeah, I did a piece out of my own sounds. I was commissioned by the Medical Museum in Copenhagen to do a piece that was based on something cellular, and I happened to know about this, and that just triggered my brain very much because I constantly looking for sound or trying to find sound that hides, and then finding out, wow, the ear that I'm using all the time, actually, could I reverse my hearing or listen to myself, to my own hearing organ? That would be like a paradox in a way. And so I found a scientist in Copenhagen, Torsten Dau, who claimed to... What's wrong here? Hello? Who could record my ears. So heavily intoxicated as well, I was put to sleep and had my ears recorded. And I didn't have much spontaneous emissions actually. But what is possible is you can evoke those tones. And that's what they also use to do to measure hearing on babies, for example, if I'm right, to play in 2 tones into the cochlea with a little tube. And these 2 tones have to have a certain ratio, 1 to 1.2. And if this interval is played into a healthy ear, the hair cells will respond with a lower tone, which can be predicted. You can simply make the calculation, say if you played at 1,000 hertz in, and then 1 to 1.2 would be 1,200 something, then you would have a slightly lower tone that could be predicted in a healthy ear.
That's the difference. That's called a difference tone?
Yeah, it could, kind of a difference tone. But because first of all, when I tried to have my ears recorded, there was not much sound, and I didn't hear much either. I couldn't hear any my own tone or anything. And as far as I am informed, that not many people can hear their own tones, which makes perfectly sense. I mean, it's a paradox, and Pythagoras, and who can hear the sound of cosmos? And you've always heard it. I don't know, but if then I had to have my ears evoked, my ear tones evoked. So I had these 2 tones played into my ear. And that's when I sat there and discovered that I could hear 3 tones. So I couldn't only hear the 2 tones that were played into my ear, but I could also hear my own ear playing.
Well, now, tonight we're not about to stick 2 tubes into everybody's ears, but we'll do the next best thing, which is to play some of this piece, which you call labyrinthitis?
Yes. There was a piece that I made for this conference, and it was based on this principle of the ear, how it evokes tones. And what I did was what you're going to hear are like the sound file you heard before, but just my ear tones that I used in the same way as the way that was used to evoke my ear tones with the sine waves, the synthetic sine waves. Instead, I took the recordings of my ears that I totally filtered so that I had these tones from my own ear, and tuned them into that interval, 1 to 1.2. And then so that when you hear these 2 tones of my ear, they should then evoke a tone in your ears.
So you'll hear 2 tones from us, and your ear, providing it's healthy, should add a 3rd tone to it.
Yeah. So since I know what tone that is that should be occurring in your ear, once that is occurring in your ear, that fades in for real, like out of the loudspeakers, and replaces those 2 tones that were used to generate that tone in your ear. And now I have this slightly deeper tone that is not generated in your ear anymore, because that tone was made by the previous 2 tones. And then I have this lower tone out of the speakers, and I add another frequency that is also 1 to 1.2, and fade those in, and then those 2 tones generate then, or trigger another lower tone in your ears that I then use again and again. So it's like an ascending composition that I then,
And sort of playing with the illusion idea that we were talking about before as well. You create the sound in our ear, and then you actually give us the sound and change it to something else.
Because I would like to question this thing about what is actually in ourselves, what is outside, and the paradox of hearing yourself hearing, because you only hear that tone when you hear. So.
All right, well, why don't we, let's hear some of it and see what happens.
Let's see. You can also move the head and back and forth, and try to listen to your own ear. Let's play it first. Did you hear anything?
Yes.
So,
did you hear? You heard the tones in your ear, yeah. It's.
So what I did was to the composition is 40 minutes long, and because what I do is to try also to make a departure from the scientific, because it's supposed to be art as well, and try to add a confusion, or not a confusion exactly, but this question about what is actually happening inside, what is outside. So I tried to do this first ascending here is based, as you might understand, on the way the ear works, basically. Then I'm also free from composing in a way, like to think about emotion and so on, and just to use what the ear does and then take that up and then play that back and then use. So at some point it came down to a point like in the frequency range where there was not much response in my own ear. I used my own ear as a, and then I start from the beginning again, but then I'm adding a canon. You know what a canon is? Singing.
A round, yeah.
Round, yeah. So once the second tone is the first tone is evoked in your ears, and then it goes on to the second tone, then a first tone is evoked in your ear as the second tone is evoked, and then that moves to the third tone, and then that moves to the second, and then another one starts. And I keep doing that until, in 40 minutes. I think in the end it's like there are like 400 frequencies at the same time. And adding all this changed the whole thing into some, like kind of another thing, and made another effect in the ear. I would like to play that for you. That's the second file.
So, Jacob, one of the interesting effects of that is when the sound fills the room, all those many different frequencies, they all kind of find their space. And if you do something as simple as this, you hear one frequency suddenly louder over here and one louder over there.
It's really interactive. You can travel, and you can decide for yourself. You can say, oh, there is a sound here. I'd like to hear that a little bit more. They're really standing in the room.
And then you sneeze, and you've moved, and you've lost it. And, but yeah, it's a fun way to sort of experience sound in space. Do you folks have drink stirrers with you? Were you given drink stirrers when you came in? Yes? Polygraph Lounge, I don't know how much science is involved in this. I assume some. But explain the drink stirrers. It's sort of related to what Jacob's been talking about.
It is. I have always been fascinated with sound of all kinds, and at a certain point in time, I became fascinated with very small sounds that are either difficult to hear or almost impossible. So I started designing a series of instruments I call microsonophones, and you can listen to them in all sorts of ways. One of them is with a stethoscope, and you're still listening to moving air as opposed to an electronic pickup. But this is my favorite kind. This is bone conduction. This is when the concert's in your cranium. So it's really private music, and you don't have to be embarrassed because no one else can hear it except you. So what we're going to do is we're going to play about 200 duets, and the only person who is going to hear each duet is each one of you. I will play with all of you, but each one of you individually will be hearing the combination of the two, and no one else. But let me teach you how to use your drink stirrer. Okay. So pick up your drink stirrer. Let's pretend you're on an airplane, and the movies aren't very good, and you've finished the novel you brought, and everyone's asleep, and there's no one to speak to. And they bring you a cup of tea, and you're left with this, or what you have. So what we're going to do is we're going to get bored, and we're going to put it in our mouth and get a good grip on it. Yeah, yeah. Now we're going to take our thumbs, very handy things, and we're just going to plug our ears like that. Now unplug your ears so you can hear the rest of the explanation. We're going to use our pinkies to play each side like a kalimba, like an African mbira, thumb piano. And you can tune it by moving it back and forth. Give yourself a low one. Let's try, everybody. Yeah. Yeah. Move it around. Find two tones you really like. It's fun to have a low one and then a doink, doink up top. Good thumbs in there. You hear it? It's huge. That's fidelity. That's high fidelity. Nothing's ever going to come close to that. Okay, now we're going to do the duets. Do we have the travel bug? Yeah. So I made one that you can all hear. This is a microsonophone I designed for airplanes with a stethoscope, but I put a pickup on it so we can all do our duets. Okay, let's all stop. A 1, 2, 3. Solo. Yeah. Bravi tutti.
So, sound in our inner ear, sound in our brain, sound in our cranium. We come back, Mark Whittle, to sound in the universe around us. Let's, as briefly as you can, give us a thumbnail sketch of how everything that we've been talking about goes back to the beginning of the cosmos as we now know it. I mean, sound really sort of imprints on how the universe was created, right?
Yeah, it does. Yes, it's funny. It's the sound sort of everywhere. All these things are vibrating all the time. Sometimes we don't perceive them, sometimes we do. But perhaps one of the most remarkable discoveries of the last sort of 10, 15 years, I suppose, has been the creation of the universe itself, this thing which one calls the Big Bang, itself had a whole slew of sounds associated with it. And I'm going to guess that we're a little short of time, so I'm just going to describe through things. Okay. So this has come to us, or rather, let me put it differently, we've learnt about it through looking very far away at this thing called the cosmic microwave background. And without going into details, it doesn't matter. Essentially, we're able to look far out and actually witness the hot, glowing gas coming from about 400,000 years after the Big Bang. We really do see it with these microwave telescopes. What these telescopes witness, remarkably, is a delicate tapestry of patches on this microwave background. These patches turn out to be the peaks and troughs of sound waves that were present in the young universe. And contrary to what you might think, which is that, well, duh, it's a big bang, clearly there's sound. You know, nice though that idea is, it is completely wrong thinking. The Big Bang actually was not an explosion into space, sending out a propagating sound wave. It's a much more subtle process. It's an expansion of space within which matter and energy are embedded, and those expand. Initially, completely silently. But one of the beauties of the process, which is thought to have actually launched this expansion, the actual, bang in the Big Bang, the launching mechanism, had at its core, had at its root, a quantum mechanical roughness to it. And so the universe emerged quiet but slightly rough, slightly denser and less dense regions, filling all of space in an expanding medium. Now, in those early times, you must remember that there were no stars or galaxies. All the matter that we now see was spread about uniformly. So although you may be thinking, well, it was space and there's no sound in space, in the young universe there is a dilute, hot, glowing, incandescent gas. So it is a medium within which sound waves can propagate. All the sound waves you've been hearing, in fact, pretty much have been driven, at least from our voices, by our diaphragm's energy, from muscular energy, or maybe strings. No, that's also muscular as well. In the case of the early universe, the driving mechanism is gravity. So that where there's a patch with slightly more matter, the gas actually falls in and then bounces out again. Falls in and then bounces out again. And so you can say in a way, I think quite literally, the universe was filled with an entire register of approximately spherical, all different shapes, organ pipes. But instead of the organ pipe being a long tube where you blow at one end and it sets up the oscillation, these are sort of spherical, so the gas is bouncing in, bouncing out again, like this. Because there's pressure in the gas, and so as it overpress, the pressure builds up, it pushes it back out, it's rarefaction, gravity pulls it back in again, so we have these oscillations going on. And I guess if we have a minute or two, I'll just play one of the sounds, so why don't we do that? I'll just set this up now. Actually, Tom, can we have some visuals there? Maybe you just want to jump to, I'm not sure which slide number this will be. No, we're going to, all right, let me just go through this. So this is, there's the microwave background with its patchiness. There are those peaks and troughs of waves. This is how we extract the sound spectrum, because I'm going to play you a sound, so I must have some knowledge of what the sound spectrum is to do that. Here it is, shock horror. It's got a fundamental and harmonics. The sound, the early universe was behaving like a musical instrument. But if you look carefully at those harmonics, they're a little fat. So don't expect to hear a clear musical instrument. There's going to be a noise quality to this, but embedded in it is, in fact, are these harmonics. I'm actually going to, because I know we're running short on time, this is, I just talked about this actually, this is the sound of gas bouncing in and out of those spherical organ pipes. I'm going to tell you that the sound there you would not have heard, apart from the fact you've been killed instantly by the light. It's just brilliant light at this time. Also, the sound is 50 octaves too low to hear, meaning one wave pulse would last about 50,000 years. So, and this little diagram illustrates why that is. The bigger the organ pipe, the deeper the note. These organ pipes were roughly 400,000 light years across. So this is one humongous set of organ pipes. Okay.
How many elephants is that?
Yeah, good one. Yeah, 10 to the 20. No, I can't quite do it. And so, incidentally, of course, this is recreational, but real cosmologists actually learn a very great deal about the universe from this. And this is just showing you how some of the properties of the universe influence the sound spectrum. So if the sound was deeper, we would learn the universe is denser. If the harmonics change a little, we can measure the amount of atomic matter or dark energy. It's a fabulous tool for probing the properties of the universe. It's a diagnostic, really. And that's what cosmologists really use it for. This was just illustrating that very fact. So sorry, going to have to, there's reality.
just blow through reality there.
Just blow through. The reality is we're running out of time. So that's the actual reality here. I'm going to pause for a moment and play this, if you don't mind. So on the right, we have the spectrum of a flute. And I've shifted the pitch up. On the left, we have the spectrum coming from the Big Bang. And I've shifted it up to match the same pitch, so our ears hear the same pitch. But you'll really see that those harmonics this is taken straight, this is from the microwave background. These harmonics, you can see, are rather fat. okay? Whereas these harmonics are pretty narrow. Tom, if we can play the flute first. Let's do this. So it's actually the same pitch, it's just the harmonics are fat, so our ears don't decode it as music. I am, in fact, going to, do you mind if we just do a little bit of this? So what I'm going to play you now, Tom, let's go to the blue one, not the one you're on, the red one. And now I'm going to have a little fun. That was the blue sound spectrum. Here we have pitch, and here we have loudness. I'm going to now make those harmonics narrow to sort of help our ears hear the chord that's actually being played. So off you go. So that's the chord within that sound. It's just extracted so you can hear it a little bit better. It's kind of interesting going back to our cultural issues. I'm going to just quickly tell you that the interval between the fundamental and the first harmonic is actually just in between a minor third and a major third. So it is, in fact, it captures, to speak poetically, it captures both moods. And in fact, as we'll hear in a moment, as the universe evolves, that tone changes, and it started out as a minor third, it evolved to a major third. How appropriate. There's a sad beginning becoming buoyant.
The happy universe we all know now.
Yeah, right, yes, it's a happy ending. It's a happy ending. So it transpires, although we can only, in fact, witness and measure the sound at a particular time, 400,000 years after the Big Bang, you may be surprised to hear that actually cosmologists thoroughly understand this entire period. And so they're able to, on a computer, reconstruct the sound. And actually, if they use those computations to match the data and therefore analyze the nature of the universe. So what I'm going to show you now is something which we can't witness directly, but we're able to actually understand how the sound developed from the Big Bang forwards in time. And so, Tom, this is where we actually play the movie. And so, you know, a lot happened in that movie, and I didn't quite set it up. So what I'm going to do is just briefly set it up for you, and then Tom, we're going to just play it one more time. So what we have here is the sound spectrum, which of course you will see changing, and as you just heard, the pitch descends for reasons we may get to in a minute. These are little trackers following the years going along. So we're just looking at the acoustic era, which is going from essentially 100 years after the Big Bang forward to about 400,000 years. That's the acoustic era. And actually, you can even witness the color of the universe. It was incandescent, but early on it was so hot, it was ultraviolet bright. And then as it cooled from expansion, it became blue hot. And then if I can do red, orange, yellow, green, blue backwards, which I'm not sure I can on the fly. But anyway, it ends up with red hot. And then, of course, it cools to today's temperature, which is 3 degrees above absolute zero, microwave hot. So there's a lot to watch. I would guess the main thing is just to listen to the pitch. But here are the harmonic sequences changing. So, Tom, just play that movie again. And that's, yeah, it's amazing. And I know it sounds a little bit like, a jet plane coming by, but the reason that is descending has nothing to do with the jet plane descending. That's a Doppler shift as the waves are compressed and then stretched as the plane flies overhead. In this case, it's to do with the fact that, unlike how we live now, you've got to recognize that 100 years after the Big Bang, there was no prior time to 100 years. So you can only excite organ pipes such that the wave could have crossed 100 light years since the Big Bang. So as time marches on, bigger and bigger organ pipes are allowed to sound. And so as time passes, this register is added to from the deepest notes, from the highest notes to the deepest notes. And perhaps the most beautiful aspect of the ideas here is that these oscillations, these organ pipes, are in fact, where it's slightly denser, that's where the gravity is going to pull the gas in, ultimately, this is going to be where the first stars form, and ultimately where the first galaxies form. And so in the last 5 years, a wonderful observational project was completed to map the positions of 1 million galaxies spanning the nearest 2 billion light years. So what we see is this mottled web-like distribution of galaxies across 2 billion light years. And when you analyze the patterns, you find the harmonic tones still present. They're not oscillating anymore, but where those organ pipes were residing, that's where there were more galaxies formed. In the troughs, where the gas was not falling in, that's where the gaps between galaxies ultimately came. The voids and the clusters and the filaments all came where the waves overlapped. So it's a fantastic matching of the current universe nearby. You notice I'm mixing proximity with time. Nearby is now. The microwave background is near the Big Bang, 14 billion years ago, but you can trace the same physics going on. You can see those early sound waves, but ultimately they spawned the galaxies that are around us now. If you'll allow me 1 more minute, I'll play the musical version of that downward slide so that we can...
Just as a quick,
yes.
You asked where the science and art overlapped. I just would like to offer...
Actually, well, I can now just skip the next 2 slides because that was pretty much what it is.
These are essentially wee organ pipes. These are fipple flutes, and
Yes.
organs are enormous fipple flutes.
Yes.
And it's precisely as you described. I'm loving this.
You know, rather than skip it, I'm just tempted to play it because you'll see I don't
please.
need to
No.
play it. So, Tom, can we just have the next
Yes,
slide
please
or two? So actually what I've done now is, with the 50 octave shift, I've now sort of, jokingly somewhat, put it onto a musical staff. And so we have, just from before, here's the piano, keyboard, bass, treble, here's the frequency, and here are our clefs. And now you can see where those harmonics are coming down. I have a slightly stretched time axis, let's not worry about that. So Tom, don't worry about it, it's time going from left to right. Tom, hit the button here. You know, I think yours was better, actually. Okay, you know, going to perception for just a second, you can't actually hear the change of chord because you're distracted by the drop-in pitch. So it's kind of nice to get into the changing chord by removing the drop-in pitch. So now I need to check about time here. Can we just play these?
Yeah, I know this is short, so
That's
let's...
the last one, so more or less. Yeah, okay.
It makes a good point.
Okay. So, so you recognize what's happened here with just taking out that downward slide. So in a sense, actually, our ears are expanding with the universe. That's what's going on here. So let's play this one, the microtonal one. And let's force it onto the tempered scale so that those notes are not allowed arbitrary frequencies. They're going to take whichever note on the piano keyboard is closest to where they should be. So that's the red one. And then for my ears, the prettiest, or the eeriest one, is repackaging all of these harmonics into a single octave, which is actually here color-coded as the blue, and up here is the blue. So let's listen to that one. And the thought I'd like to leave you with is that those tones ended up spawning the first generation of stars, which then formed the galaxies that we now inhabit. So in a really delightful sense, music is really with us right from the beginning, crafting the structures which we now see around us.
And in a funny way brings us back to an idea we started with, which was, you know, Jamshed talking about the imperfections in Pythagoras' cycle of fifths, and you go through the fifths, and there's that little comma there, and the imperfections in the expanding universe creating galaxies and stars out of sound. It's an amazing, and as you say, a very poetic thought to leave it with. Let me thank all of you for being with us tonight. It's really been an extraordinary journey in sound, both inside our heads and out. And I want to thank everyone here for being with us as well. And Polygraph Lounge, would you guys play us out with something? Again, thank you all.
So it makes sense to talk about the sounds that surround us, the sounds all around us, and they're the sounds that found all of us today, tonight. It's like this. The sounds that surround us are the sounds all around us, 'cause they're the sounds that found us today. Yeah. There goes the taxi. Here comes a bus. Man, oh, there goes a fire truck. Yeah, went right by us. Man, listen to the wind blow. Yeah, listen to the rain. Listen to the thunder. Sounds like a train. The car goes honk, 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 honk. Your mother says that's so annoying. And it really is when they honk like that. The jackhammer goes rat tat 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 tat. I mean, what's that? It's the sounds that surround us. It's the sounds all around us. 'Cause they're the sounds that found us each day. Yeah. Tea kettles when they're whistling, clocks are going tick-tock. Babies when they're crying, yeah, neighbors when they knock. Oh, listen to the waves crash, yeah, listen to the birds. Listen to my dog howl, it's a song without words. The windshield wipers on the bus go back and forth and back and forth and shh, 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 shh. The cell phone rings, the owner answers, blah, 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 la, 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 'cause they're the sounds that surround us. They're the sounds all around us, 'cause they're the sounds that found you today. And every day, they're the sounds that found us. Hooray, hooray for the sounds. And listen, tonight we've listened to the sound of science.
Polygraph Lounge, thank you all. Good night.